Hey, welcome back to your favorite calculus class. We're going to talk about differentiation rules today. We're going to introduce several rules that allow us to differentiate constant functions, power functions, polynomials, exponentials, and so on, so that we don't have to run the limiting process every time. This is the section where everybody goes, "Why didn't you tell us that before?" And the reason we didn't tell you about the rules before is because we want to go through that limiting process so that you understand how that connection is made in the conceptual approach as we establish this dynamic mathematics as compared to the very static mathematics that pre-calculus is. That's the connection. That limiting process is the connection. So let's start out with the derivative of a constant. Okay, so the derivative of a constant. Let me give you an example. Let's take f of x equals 7 for a minute. We know that here's y equals 7. And if we're finding the derivative of that, the derivative f prime of x, we know the slope of the tangent line anywhere on here, the slope is always what? Well, the slope is always 0, right? So the derivative of constant is always, the derivative of a constant, the derivative of any constant is always going to be 0, right? The slope of the tangent line is going to be 0. So here's your proof of that. Limit as h goes to 0 of f of x plus h minus f of x all over x plus h minus x, right? So we have f of x plus h, so I plug x plus h in for x into the function. Well, there's no x to plug into, so we just have 7 minus the original function 7 all over h, limit as h goes to 0. So we got 0 over h, which is just 0. So the derivative, f prime of x, is 0. So if f of x equals 7, f prime of x must be 0. So the derivative, anytime you have a constant, any constant, the derivative of a constant is 0. Okay? All right, now here's the power rule. Not only does this work for any positive integer, this works for any n real number. Okay? And here's the proof of that using the alternate form of the derivative. Limit as z goes to f of z minus f of x. So what happens is if we factor out a z minus x, top and bottom, then you're left with this right here. The z minus x is canceled. That's what you're left with right there. Okay, and then that cleans up as z becomes x. Limit as z goes to x, you'll get the nx to the n minus 1. Let me give you an example with f of x equals x cubed. Okay, so first of all, the rule is that the derivative of anything of the form x to the n, where n is a real number, is nx to the n minus 1. Okay, so for this one, the derivative would be 3, so the n goes in front, x to the 3 minus 1, so 3x squared. Okay, that's the derivative according to the rule. Now, to prove that, we'll just use the alternate form of the derivative and show you how that works. And we'll show you that you actually get 3x squared. So this becomes limit as z goes to x, f of z. Remember, f of x is x cubed, so that'll be z cubed minus the original f of x, which is x cubed over z minus x. And now we factor a cubed minus, we got a cubed minus b cubed on the top, right? Which is a minus b, so z minus x. Whoops, that's an x, z minus x. And then a squared plus ab plus b squared, so z squared plus zx plus x squared, if you remember how to factor a cubed minus b cubed. So we got z minus x on the bottom. There goes our z minus x's. And then we're going to take the limit as z goes to x. All right, so now we're going to plug in x for our z's. X for our z's right there. So this becomes x squared, instead of z squared, plus x times x, again that z becomes x there, plus x squared. Excuse me. So we got x squared plus x squared plus x squared, 3x squared. There's the derivative. See that? So there's the limiting process, right? This is the limiting process. But now we don't have to do it. We have the rule. So we can just follow the rule. You know, for example, if we have y equals x to the fourth, then dy dx, the derivative, is 4x to the 4 minus 1. 4x to the third. We don't have to run that limiting process anymore. If I want to take the second derivative of that, then, oh, you know what? I haven't introduced the constant rule yet in front there, so let me hold off on that. Y equals x to the negative 5. Y equals x to the negative 5. If I'm going to run, I'm just trying to use different notations for you guys. If I run the derivative on both sides here, so I have dy dx equals negative 5x to the negative 5 minus 1. So negative 5x to the negative 6. Or negative 5 over x to the 6th. There's dy dx. There's some more. The derivative of x cubed, 3x to the 3 minus 1, 3x squared. That's a b. The derivative with respect to x of x to the 2/3. Again, using the rule, 2/3 x to the 2/3 minus 1. There's, in other words, minus 3/3. So we have 2/3 x to the negative 1/3. C, x to the square root of 2. We're going to take the derivative of that. So that's root 2 x to the root 2 minus 1. And we're done with that one. D, 1 over x to the 4th. What I'm going to do before I do that is I'm going to rewrite that as x to the negative 4. I gotta have it in the form of x to the n before I run the rule. Okay, so I get it in the form. So instead of 1 over x to the 4th, I'm going to think about that as x to the negative 4. And then I'll run it. Negative 4, x to the negative 4 minus 1 is negative 5. So that's negative 4 over x to the 5th. And then E, got negative 4/3 x to the negative 4/3 minus 1. So negative 4/3 x to the negative 7/3. All right, derivative, what if you have a constant and then the function? So you can, if you think about the limiting process, right, you could put the constant out front and then take the derivative of u, and here's the derivative part. So it's just c and then the derivative. Okay, so for example, I have here the derivative of 3x squared. So the derivative, the 3 stays in front. Now I just take the derivative of x squared, which is 2x to the 2 minus 1. So 6x to the 1 power. If we could take, that's the first derivative, right? So if y equals 3x squared, the first derivative, dy dx, is 3 times 2x, so 6x. If they ask for the second derivative, so the derivative of 6x, now we can take that second derivative. So 6 stays there, take the derivative of x. Now this is x to the 1 power, so it'll be 1 x to the 1 minus 1. So 6 x to the 0. Well, anything to the 0 is just 1. So this is just 6. In fact, a lot of times people will even write this as if it's a rule, right? But this is still following the power rule. The derivative of x is just 1 because it's 1x to the 0. It just ends up being 1. Okay, so that's what happens with the constant. Leave the constant there, take the derivative. All right, if you've got a summation, right, like if you have x cubed plus x squared and you're taking that derivative, then you just take the derivative of the first, 3x squared, plus the derivative of the second, 2x. Okay, that's what this is saying. Same thing for a minus. All right, derivative of a to the x or a to the u is ln of a times a to the x. So an example would be e to the x as an example of this. So your base is e. So following this, it's ln of e times e to the x. Well, we know that ln of e to the 1 is just 1. So the derivative of e to the x just ends up being e to the x, but it's following the rule there, right? Here's another one over here, derivative of 2 to the x, so our a is 2 here, so that's ln of 2, ln of a, and then 2 to the x. Now this is called the product rule, okay? And I like this. I like it in the function notation form. So the derivative of f of x times g of x is derivative of the first times the second plus the first, leave it alone, times the derivative of the second. Okay, so for example, let's do it here. This is h of x equals, this is my f of x, that's my g of x. So what I'm going to use is the derivative is derivative of the first, so f prime of x, times the second, leave it alone, plus the first, so you leave it alone, times the derivative of the second. So that's what I'm going to follow here. So h prime of x is derivative of the first. So I'm taking the derivative of this one. Derivative of 3x is just 3 minus 2, so that's the constant part. Now I'm taking the derivative of x squared, which is 2x to the 1. Okay, there's f prime of x times g. So I just leave this alone. 5 plus 4x. Okay, so I've done f prime of x, and then I just left g of x alone. Just left g of x alone. Plus, now I leave f of x alone. So I just write 3x minus 2x squared. And then I take the derivative of g of x. So I got to take the derivative of that one. So derivative of 5 is 0. And then plus 4 derivative of x is just the 1. So here's f of x, and this is g prime of x. Okay. So we've got 3 minus 4x times 5 plus 4x plus 3x minus 2x squared times 4. Okay. So now we just clean this up. So I got 15 plus 12x minus 20x minus 16x squared plus 12x minus 8x squared. X squared, so I got negative 24x squared. 12 minus 20 plus 12, that's what, plus 4x, and then plus 15. So there's h prime of x. Okay? You know what? Why don't we do the second derivative on that? You can take the second derivative here, so h double prime of x, the second derivative. Now I leave the negative 24 there, and I take the derivative of x squared, which is 2x, now it's to a 1 power. Plus, I leave the 4 there, I take the derivative of that x, which is 1, derivative of 15, 0. So negative 48x plus 4 would be the second derivative there. Alright, this is the quotient rule. So the derivative of f of x over g of x is derivative first times the second minus now the first derivative of the top, derivative of the numerator times the denominator minus the numerator times the derivative of the bottom all over bottom squared. Okay, so I remember it as derivative of the top times the bottom minus top derivative of the bottom over bottom squared. That's how I think of that. Okay, that's how I remember it. At least I'll write it over here. So if the derivative of f of x over g of x is derivative of the top times the bottom, oops, minus the top, derivative of the bottom, all over bottom squared. Okay, so that's what we're going to follow. So y prime is, so the top is 5x minus 2. So I take the derivative of that. Derivative of 5x is 5. Derivative of minus 2 is 0. Okay, there's the f prime of x. Now I'm taking the derivative of the, now I'm just leaving the bottom alone. I'm sorry, I'm doing the g of x part. Okay, I already did that. Derivative of the numerator. Now I'm just leaving g of x alone, so I just put it right next to it. X squared plus 1. Minus. Now I have the numerator is my f of x. So I just leave this one alone now. Times the derivative, g of x, so I've done that one. Now I'm taking the derivative of the denominator. Derivative of x squared, 2x. Derivative of the plus 1, 0. Okay, so I've done derivative of the top times the bottom minus the top derivative of the bottom over bottom squared. So that's how I remember the little pattern. So y prime equals 5x squared plus 5 minus 10x squared plus 4x over x squared plus 1 quantity squared. So I got negative 5x squared plus 4x plus 5 over x squared plus 1 quantity squared. There's the derivative, first derivative. And of course, you could do the second derivative as well. All right, I'm going to do a quick little chain rule, just an introduction. We're actually going to visit this later in more depth, okay? But if you have a composite function, like let me give you an example. Instead of like just x cubed, you know, we know that derivative is 3x squared. What if it was a composite like 2x quantity cubed? In other words, f of x is x cubed and g of x is 2x, because this is a composite f of g of x. In other words, 2x is going into f, right? 2x is going into f, and we know f is x cubed. What's going in? 2x is. You see how this is a composite function? So it's a little different. So according to this, if you have f of g of x, when I take the derivative, it's f prime of g of x, and then it's g prime of x. So this derivative is 3, 2x to the 3 minus 1, 2, and then I take the derivative of the inside, which is 2. So it's f prime of g of x, f prime of g of x, that's this part, and then it's the derivative of the inside. So the derivative of 2x is just the 2 right there. So it cleans up to be 6, 2x quantity squared, or that's 4x squared, or 24x squared in this case, right? Over here, we've got another composite function. Right, our f of x is e to the x. Our g of x is negative 6x. So, and what we need to remember is the derivative of a to the x is ln a to the x, right? Don't forget that. So this becomes, when I take this derivative, it's ln of e. This stays the same, e to the negative 6x. But notice, it's not just an x up there. This is a composite function. It's negative 6x. So I got to take the derivative of negative 6x, which is just negative 6 times the derivative of x, which is 1. ln e is just 1, so this just becomes negative 6 e to the negative 6x. And that's your y prime. That's your derivative. Okay, let's do another one here. Again, this is a composite function. F of x is x to the negative 1, or g of x in this case is 2x minus 7. Alright, that's going in there. So the derivative, dy dx, is, I run my power rule, so negative 1 goes there. This stays, oops, 2x minus 7, I'm sorry. and then it's negative 1 minus 1, so negative 2. Okay, so what we did is we took f prime of g of x. It's kind of like we just did this, right? But notice it's not just x there, it's 2x minus 7, right? It's f. Remember, when I take the derivative f of g prime of x, it's f prime of g of x, g prime of x. So I got to remember to take the derivative of the inside now. So derivative of 2x is 2, derivative of that is 0. So this ends up being negative 2 over 2x minus 7, 20 squared. There's our derivative on that one, okay? All right, well, a little bit of notation at the end here. We kind of used some of these today, but we have, here's a first derivative, here's a second derivative, here's a third derivative, and so on. You could go to a fourth derivative, whatever. Y to the, super n there on that. You don't see that a whole lot. Say dy dx, that's a first derivative. This is a second derivative, and so on. Lots of notations, take the derivative of whatever you're taking a derivative of, and so on. This thing you don't see a whole lot, but all notations. Well, thank you so much for watching and taking notes. We will see you guys next time.